So let's come back to this Sard's theorem. So Sard's theorem. See why Sard's theorem is important, because it talks about x to y. What does it say? That if you have a morphism, say f from x to y, so on an open set it is fine. The fibers are fine. Right? That's what it says. That it's a morphism of algebraic varieties. You can assume dominant morphism, because otherwise you will have some point whose inverse image is empty. So they are not so interesting object. So then there exists a characteristic 0. Base field is characteristic 0. So there exists an open subset U y such that f, when you restrict to this f inverse of u to y or to u is a smooth map, or is a smooth map, in other words, that way for every x in u or every y in u, that is every y in u, f inverse of y is smooth. So this is a generalization of the concept that smooth points are most points in an algebraic variety, given algebraic variety, the smooth points are dense. Right? The bad point, which are non-smooth point, they are closed. So the complement is smooth. So this is if you take y to be point, for example. Right? So this is a generalization of that. Of course, it is a difficult theorem, because even in the case of when y is spec k, you saw that it required some effort, right? It was not easy to prove that singular set is a closed set. So here also you require some technique. So first of all, observation. So this is a question of smoothness. That means so what do you mean by smooth? F is smooth means tangent space level the map is surjective, or this F is generically surjective at the tangent space level. So that means without loss of tangent space level means at a point. So we can, without loss of generality, we can assume x and y are affine, because after all these are all, any variety is you get it by patching, by union of affine varieties. So without loss of generality, one can assume x, y affine, and since f is dominant, so f of x, dimension of x and dimension of y is f of x closure is y. Or in other words, this is same as saying that so this will imply that dimension of x is greater than equal to dimension of y. So there is some relative dimension. It may be 0, it may be positive. Relative dimension means dimension x minus dimension y. That is called relative dimension. So relative dimension is positive. Right. So now I need to say that f inverse some point over an open set, f inverse of x is smooth. So it is enough to show that over an open set. So enough to show over an open set the map is smooth. The map f is smooth. That is this U2, there is a open set here, non-empty. At the point Tx of this f inverse of u to t of fx at y or tf or u. This map is surjective. Is surjective. The good thing about tangent space, this definition, is that this is a vector space map. So ultimately, this is some kind of linear algebra. See, morphism is very complicated, right? X to y, the morphism is a very complicated object. But if you want to study, so it is a tangent when you even in that the +2 level when you study differentiation. So it the derivative gives the information of the at that point or local description. This is also same what it is saying. But the good thing about tangent space or tangent bundle, it gives you can do some linear algebra, linearization of your function in some sense. So this map, this df, you can think as this is some kind of a linearization of your morphism f. F may be very complicated function, it may not be linear, but this map is linear. That's a good thing. So sometimes it is easier to study tangent space than the actual morphism, right? So now since this is since x and y are affine, now the point is, now what we know, you have to show that at a generic level the tangent space is surjective. Okay. So now what is given? See, you must have seen that if x is an affine variety, this is just normalization lemma. If x is affine variety, say x is dimension of x is 1, n. So this is over affine variety over k, say base field is k. So that means this is same as saying that transience degree of the function field kx over k is n, right? In this case, you know that there is a you know that there is a surjective map from x to an. Noether normalization says that, right? Why? Because you consider this Ax, then what you know, there are some elements say Z1, Z2, Zn, which are algebraically independent, such that this Ax is a finite module over k Z1, Z2, Zn. So this is a subring because Z1, Z2, Zn is in Ax, right? So you consider and then this is a Ax is a finite k Z1, Z2, Zn module. Finite means integral. So integral now, if you take the functor, the opposite functor, so these are finitely generated k algebra. If you take the opposite functor, what you get? You will get a map from x to, because these are Z1, Z2, Zn, you can think as a very variable, right? Because they are algebraically independent. So there is a map from x to n, and this map is surjective because of integrality. A maximal ideal here it will come from maximal ideal here. So the map is surjective. When you have an integral extension, maximal ideals is coming from the maximal ideal, right? So this is always a surjective map. Now the point is that here it is at the, so you started with something x over k or spec k, right? So here, so any variety, I always can think, if x is a variety, I can always think as a morphism x to point. This you always say, so a variety Ax and we always think, you can think always in this language, right? So now what we have to do? We have to do something like a relative so suppose it's not a point. So now what we have? We have a map something like x to y. Now, can we have questions that can we have a normalized Noether normalization for such? What is a generalization for at the relative Noether normalization in some sense? So this is the at over spec k, but over a ring. So x and y are all affine varieties. So this is same as say if you call this ay and if you call this ax, right? So x to y, if you have a morphism, then ax is a ay algebra, right? So you have a map from ay to ax. So the point is that if you have, so when a, so yes, can we have Noether normal, something like Noether normalization? So I will write the first the statement, then probably it will be clear. So let me write it. So let's write ay equal to d, say, and ax equal to r, and we have a r is a d algebra. So the theorem, so the generalization of Noether normalization okay, suppose D is a domain and R is a finitely generated D algebra. Then there exists a non-zero element C belongs to R, no, C belongs to D, belongs to the ring, C belongs to D, C belongs to D, and Z1 D belongs to R such that Z1, Z2, Z1 are and they are algebraically independent. That means they form a transience basis such that RC, the localized, RC means the localization, RC is integral or finite module or finitely generated module over DC. So now the only difference with it is that the C is not over the entire D. So what it is saying that, so you have D and you have D is sitting inside DC. So this is a localized domain, right? D is sitting inside DC, and R, these are all affine varieties. So this will induce this map DC to RC. So what it's saying that RC is a finite module over DC Z1, Z2, Zn. Right. So that means, so this is, I can write DC and DC is sitting inside Z1, Z2, Zd. Because these are all finitely generated, right? Affine varieties, X and Y. So I am starting with, because X and Y are finite. So X and Y, they are finitely generated K algebra. So if you have a morphism x to y, then y also has to be finitely generalized. So now the point is this RC is a finite module over DC Z1, Z2, Zd. Now you see in the case of when y was a point, and then C is in D was K, right? So what is DC? DC is nothing but K itself. So you get the original Noether normalization back when D equal to K, because C after all is invertible. But here the point is that you don't get this Noether normalization over the entire x comma y, but on an open set, because this is DC after all localization. This is an open set. So in localization of a ring is a regular function on a smaller. This is a bigger ring, right? So that means this is the corresponding regular ring for a smaller open set. So you have Noether normalization for over an open set. So that means so what does it say? That means this x prime you have, if this x prime, this corresponds to this corresponds to this, and this y prime, not this one, sorry, the other one, this one. The x prime will correspond, because it's opposite functor. So x prime will correspond to this RC, but that is that will be in the open subset of spec R. So this will be an open subset here, and this is, now if something is integral means it's a finite. So then x prime to y prime, this map is finite. So given, sorry, and not this is x prime, but this is not just x prime. X prime is DC. Sorry, this is not just y prime. This is y prime with Z1, Z2, Zd. So that means y prime tensor with AD, right? Y prime tensor with AD. Right? This is a finite module. So RC will correspond to this x prime, and what is this? This will correspond. This will correspond to y prime tensor, because DC will correspond to some open subset in D. So this is y prime tensor with AD. So that means tensor means this is cross. So given a morphism x to y, so over an open set, I can think this is as a map from x prime to y. If I restrict to an open set, this map looks like x prime to y prime cross AD, the affine space. Right. So that means the morphism which I have started with x to y. So in this case, if I apply this x to y I started with, so what I get to open subset y prime, and this is f. F takes x prime to y prime. I have a diagram like this, that x prime to y prime, and this is x prime cross AD, where D is the relative dimension. So this is nothing but dimension of x prime minus dimension of y prime, which is same as dimension of x minus dimension of y, because we are considering these are irreducible. Dimension of an open set is same as the dimension of the under closure, and this is x. Sorry, this is not y. It is y prime, and this y prime to y prime. This is the projection map. So we are in this situation. So this means that this is the relativization of Noether normalization. That if I start with a morphism x to y, I can but now this map, so what, and this map is a finite map, we know, that's what we saw. But now the point is that what I want to prove, I want to prove that if I take a point here, or at least at an open subset, I want to prove that this Tx x prime to T f of x y prime, this map is surjective. But this map is a finite map. Now finite map are generically étal. Generically étal means that generically these tangent spaces are isomorphic, because finite maps means the fibers are finite, but at some point there may be some collapse. But those points will be because most points, like in last class I was saying that most points are separated. If you have a finite maps, most points are separated. There are some points which will collapse to one point. They are ramified points, but most of the points they are isolated. So that means, and this is a finite map. So dimension of x prime and dimension of this is same. So at most points, so in the x prime, you have an open subset where the tangent spaces are isomorphic, right? If their dimensions are same, and or those generic points where there is no collapsing, so the tangent spaces will be isomorphic. So over an open subset, so over U, so there exists a U. There exists a U in x prime where this Tx of x prime to the, if I call this map G, T of Gx of y prime cross AD, this map is isomorphism for all x belongs to U. Because after all, it's a finite map, right? Fibers are finite. So at some point there may be some collapse. So tangent space level there may be some mismatch. But most of the points, the map is like a local isomorphism or locally étal, right? So now, so there it is isomorphism, and this is a projection map. So this map is surjective. So Gx will go to f of x. So this map is surjective. This is isomorphism and this is surjective for all x. So that will say that this is a surjective. So done. So see, Noether normalization, not in the exact form, but you have to little bit tweak it. Noether normalization. And you get a Sard's theorem. But this is in characteristic 0. Noether normalization will be true, but this tangent space and all, there are examples where all points are singular. I mean, all fibers are singular. We have seen some example, right? Because whenever you take differential, they go to 0. So, but the space is a non-trivial space. So tangents, there is some tangent space. So it is not a surjective map. The differentials are all 0, but it is after, but it's not a point. It is surjective. If it is the differential map is 0, and then it has to be a point, but it is not a point. It's algebraic variety. So there will be some tangent space, right? So that's why it is not a smooth map. Yeah. Okay, so this is Sard's theorem. So we saw so application of Sard's theorem in last class. We saw that it's a Bezout's theorem, is a Bertini's theorem. So now in the next few lectures, I want to do give some at least some cases where, see, the problem with the, now little bit I will say now, maybe in next lecture I will continue. The problem is main problem is the functoriality. See, always you have to do this. Whenever you have a map of variety or map of scheme, you have some, even in the case of affine variety. So if Ax, for example, the coordinate ring, if it is Ay to Ax, Ax is a Ay algebra, right? But if Ax is not reduced, what will you do? You cannot, right? So this is one problem when the coordinate ring, if you start with, so if you start with some K algebra which is not reduced, or sometimes it happens that when you take something xy, if you take some fiber, it may not be reduced. There may be nil radical. So they appear in commutative algebra. Even if you start with everything as a good domain and reduce, but after this many algebraic operation, this kind of nil radical they appear, and the resulting ring. And then what you do? I mean, you cannot do geometry with that. You cannot do it in this way. So you have to include them. So best way to include them is to talk about scheme theory. So you don't talk about just maximal idea, you talk about prime ideals also. And it is very functorial in the sense that there is because maximal idea only in the finite case only, you know that contraction of maximal idea is always a maximal idea. It may not be always, right? So in that case, what happens? So you lose the functoriality. So then you study schemes. Schemes are more functorial. You can do geometry more. You have more freedom. Everywhere you have to, because whenever you get some ring, then what you have to get a variety size, you have to consider the A reduced. A reduced, which is nothing but A by nil radical of A. So you lose some information in some sense in the coordinate ring. For example, if you have this ring like kx mod x power n and kx mod x, suppose k is algebraically closed. So one is both are point, but this ring and this ring there is a difference. One has nilpotent and one so how do you take care of these nilpotent elements? Right? If you have some function like v of x square and v of x, but this has, if it is 0 of x square and 0 of x should be thought of differently. They should not be same because that is the problem. I mean, you don't see if a dot b equal to 0 does not imply always that a equal to 0 or b equal to 0. In characteristic P we have seen, right? In characteristic P, I mean, it's quite a phenomena. So maybe in next 2 class I will just talk about some scheme theory, why it is important and why one should study. and I will stop there.